Think of it like two halves of a grand cosmic story that have never quite aligned. On one side is the quantum realm, restless, jittery, immeasurably small, where particles shimmer between existence and non-existence like fleeting thoughts. And on the other side is the majestic universe of stars and galaxies, shaped by the steady pull of gravity, the bending of space-time, and vast cosmic structures stretching across billions of light years. Both stories are true. Both stories describe our universe with breathtaking precision, yet when we try to combine them, they refuse to fit. They contradict each other at the most extreme places. Black holes, the Big Bang, the earliest moments of time. Tonight, we begin a slow, deep exploration of humanity's boldest scientific quest to bridge these two halves of reality and reveal the unified story behind everything. This is the quest for quantum gravity, a journey into the smallest distances, the highest energies, and the deepest mysteries of existence. And now, our journey begins. Chapter 1. The universe's biggest contradiction. Two worlds, one problem. Think of the universe as a grand tapestry, an enormous cosmic narrative woven from two entirely different threads. Each thread tells a magnificent story, rich with beauty, accuracy, and depth. Yet, when we try to weave them together, they refuse to form a seamless whole. The edges fray, the stories diverge, and the universe, which should be a unified masterpiece, becomes a mystery with two clashing voices. On one side lies quantum mechanics, the astonishing and unsettling language of the microscopic world. Here, particles are not solid entities, but shimmering possibilities. They flicker into existence like fireflies appearing in the dark, governed by probabilities instead of certainty. Reality is fluid, causes are questionable, effects appear before reasons. In this strange realm, the universe behaves like a game whose rules are rewritten the moment you look at them. On the other side stands general relativity, elegant and majestic a theory of gravity that shapes the entire cosmos. It treats space and time not as empty containers, but as dynamic, living entities. According to Einstein, mass and energy warp the geometry of the universe, bending trajectories of planets, shaping the birth of stars, and guiding galaxies like dancers across the cosmic floor. Everything flows smoothly, continuously, predictably. Each theory reigns supreme in its own kingdom. Quantum mechanics explains the subatomic world with astonishing precision: electrons and orbitals, radioactive decay, lasers, the behavior of semiconductors, and everything that powers modern technology. General relativity governs the cosmic landscape: black holes, galaxies, gravitational waves, the curvature of space-time itself. Their predictive power is unmatched. Their success is undeniable. Their beauty is breathtaking. And yet, when their worlds overlap, when we ask them to describe the same event at the same time, they fall into a irreconcilable conflict. The equations refuse to align. The results become absurd. They simply cannot both be right in the extreme corners of the universe. This contradiction is not a small detail. It is the fracture line across modern physics, the greatest unresolved tension in our understanding of reality. It is a puzzle that suggests something profound. The universe is whispering a secret we have not yet learned to decode. This is the doorway to quantum gravity. This is the beginning of our story, where physics breaks down. For most of the cosmos, our two great theories coexist peacefully, each governing its domain with masterful accuracy. But scattered throughout the universe exist rare realms of unimaginable extremes, places where nature pushes beyond all limits, where density grows ferocious and gravity becomes titanic. These environments are so intense that neither of our theories can survive intact within them. Consider a black hole. At its center lies a region where matter is crushed to inconceivable density, where space-time curves infinitely, where gravity becomes so overwhelming that not even light can escape. Here, quantum mechanics demands that particles never truly disappear into a mathematical abyss. But general relativity insists that everything collapses into a singularity, a point of infinite density, infinite curvature, infinite breakdown. Two great theories, two incompatible predictions, one cosmic battleground. Or consider the Big Bang, the origin of everything. According to general relativity, the universe began from a singularity, a point smaller than anything we can imagine, hotter than any furnace, denser than any star. But quantum mechanics tells us the very notion of a singularity is physically impossible. It claims that at that scale fluctuations dominate reality, uncertainty reigns, and nothing can be compressed into a literal point. The equations explode with infinities, warnings that something is wrong, something incomplete, something missing from our understanding. Instead of describing the universe, our theories collapse under their own contradictions. In these moments, the birth of the universe, the death of stars, the edge of black holes, physics stops working. The mathematical languages we trust suddenly stutter, halting mid-sentence, as though refusing to continue the story. And this is not a minor issue. If our theories cannot describe the most extreme environments, then they cannot be the final word. They cannot be the ultimate blueprint of reality. The universe is telling us. These tools were only first drafts. These breakdowns highlight a profound truth. Modern physics is an unfinished puzzle. Two pieces fit perfectly on their own, but snap and crack when forced together. To understand the cosmos fully, to reach the heart of black holes, to understand the true beginning of the universe, we need a new frame of understanding. A theory that does not break at extremes. A theory that embraces both the quantum and the cosmic in one unified breath. Why unification matters. Why chase unification at all? Why insist on merging two theories that seem content to rule their separate kingdoms? Because history shows us what happens when we unify ideas. Every time humanity has succeeded in merging separate principles into a single framework, the universe has revealed deeper truths. We gained the insight needed to understand gravity in a new light, one that changed our picture of the cosmos forever. When energy and mass merged into E equals mc, we understood stars, nuclear power, and the engine of the universe itself. Unification is the engine of scientific progress. It is nature's way of hinting that simplicity lies beneath complexity. If we succeed in merging quantum mechanics and general relativity, we would possess a single worldview capable of describing everything from the smallest vibrating particle to the largest galaxy cluster. Such a theory could reveal the true nature of time, what really happens inside a black hole, why the universe began the way it did, whether space is continuous or discrete, whether reality emerges from something deeper than space-time. It could point us toward new physics, new technologies, new understandings of existence, and perhaps it may reveal aspects of the universe we have never imagined, hidden dimensions, new forms of matter, or even new laws that transcend the current limits of science. Unification isn't just an academic challenge, it is the pursuit of a deeper harmony that underlies all of nature. A belief that beneath the swirling diversity of physical phenomena lies a single, coherent truth. This pursuit is not optional. It is the destiny of physics, the rift between continuity and randomness. At a philosophical level, the conflict between our two great theories mirrors a deeper divide, the clash between a universe that is smooth and continuous and one that is jittery and discrete. General relativity imagines the universe as a serene ocean of curved space-time. Everything is smooth, everything is continuous. Objects follow graceful trajectories influenced by the shape of space. Time flows steadily, rhythmically, universally. Quantum mechanics, by contrast, depicts the universe as a place where energy comes in packets, where positions blur, where events occur in sudden bursts rather than steady transitions. It's a realm of jumps and jitters, of wild fluctuations and constant uncertainty. It's the difference between a flowing river and a churning sea of bubbles. The difference between a steady melody and a chaotic, unpredictable rhythm. Trying to merge these two pictures feels like trying to unite water with sparks, two different textures of existence, and yet we know they must be related. The universe cannot operate with two contradictory rulebooks. Somewhere beneath the confusion lies a deeper structure that harmonizes the smooth with the discrete. Perhaps spacetime is continuous at large scales but pixelated at small ones. Perhaps matter emerges from geometry, or geometry emerges from matter. Perhaps both theories are approximations of something more fundamental, something neither is captured in full. This rift is not just a mathematical anomaly, it is the philosophical epicenter of the mystery. What is the universe made of? What is the true fabric of existence? Until we resolve this contradiction, we cannot claim to understand reality not fully. Setting the stage for the journey expanded, we have reached a threshold. The contradiction between the quantum and he cosmic is no longer a curiosity. It is the most important unresolved question in physics. It is the gap we must bridge if we hope to understand the grand structure of the universe. In this chapter we've mapped out the battlefield. Two unmatched theories, each miraculously accurate, places where they collapse into failure. The philosophical divide between continuity and discreteness, and the stakes nothing short of the blueprint of reality. Now the journey deepens. Beyond this point we shrink ourselves down to the Planck scale, the tiniest arena in the universe, where space-time may stop behaving like a smooth fabric, and instead reveal itself as grainy, foamy, restless. Once inside this realm, we encounter two great visions, two competing frameworks that attempt to describe quantum gravity. One says space-time is woven from discrete threads. The other says everything is vibration strings singing reality into form. Loop quantum gravity and string theory, two bold paths, two radically different perspectives, both reaching toward the same unreachable truth. Our journey into quantum gravity begins now. Chapter 2, The Quest for a Quantum Realm of Gravity, the Graviton and the Quantum Face of Gravity. To understand quantum gravity, we must begin by stepping into a world that is far smaller than anything our senses can grasp. A world beneath atom, beneath quarks, beneath even the tiniest structures known to physics. A world where the rules we take for granted begin to dissolve, replaced by something stranger and far less intuitive. In this realm, particles behave like notes in a cosmic symphony. Every force in nature, except gravity, already has a quantum explanation. Electromagnetism is carried by photons, the strong nuclear force by gluons, the weak nuclear force by W and Z bosons. Each of these forces is represented by particles' tiny quanta that transmit interactions in discrete packets. This picture has explained nearly everything in particle physics with astonishing accuracy. So it is natural to imagine that gravity, too, must have a quantum particle behind it. Physicists call this hypothetical particle the graviton. A graviton would be massless like a photon, incredibly weak in its interactions, able to travel at the speed of light, carrying the quantum of gravitational force. But gravity differs from the other forces in one crucial way. It isn't just a field on space-time. It is the shape of space-time itself. To quantize gravity means to quantize the geometry of the universe. It is like trying to quantize the stage on which the other forces perform. Instead of asking how particles move through space, we're asking how space itself behaves when viewed under a quantum microscope. This leads us to a profound question. What does space-time look like when examined at the smallest possible scale? As we shrink down, empty space is no longer smooth. Distances become uncertain. Time intervals jitter unpredictably. The geometry of the universe begins to ripple with quantum fluctuations, like a restless ocean stirred by invisible winds. At everyday scales, gravity feels solid and predictable. But at the tiniest scales, it may behave like a wild, feverish thing, dancing, fluctuating, refusing to stay still for even a moment. This shift marks the beginning of the quest for quantum gravity, the attempt not just to describe the forces within the universe, but to understand the quantum nature of the universe itself, the Planck scale, where space-time disintegrates. If you were to zoom down deeper past molecules, past atoms, past the nuclei at their hearts, you would reach distances so small that the entire structure of reality begins to tremble. This is the Planck scale, named after Max Planck, the father of quantum theory. It represents the smallest scale at which our current physics has any meaning. The Planck length is roughly 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000. A decimal point followed by 34 zeros and a 1, a scale so unimaginably small that even comparing it to an atom fails to convey its tininess. If an atom were the size of the observable universe, the Planck length would be about the size of a tree. Here, the geometry of the cosmos undergoes a transformation. Space-time becomes grainy and foamy, seething with quantum uncertainty. This isn't the smooth space-time of Einstein's equations. It's a frothed sea of randomness, bubbling, shifting, flickering in and out of existence. Distances are no longer definite. Time no longer flows smoothly. Energy surges unpredictably. This chaotic turbulence forms what physicists call quantum space-time foamy landscape, where tiny wormholes may appear momentarily, virtual black holes may blink in and out of being. Dimensions might twist and recoil, and causality itself becomes fuzzy. Trying to apply general relativity in such a realm is impossible. The equations break apart. Trying to apply quantum mechanics alone also fails. It assumes a fixed background, which no longer exists. We stand at the edge of a precipice in our understanding. We must invent new mathematical tools, new concepts, new models that do not yet exist. This is the frontier where theories like loop, quantum gravity, and string theory emerge. To understand the Planck scale is to stand at the boundary of the known universe and to peer into the unknown, quantum foam, and the turbulent nature of reality. Quantum foam is not merely a theoretical idea. It is the closest glimpse we have into the raw, unfiltered behavior of space-time at its most fundamental level. If you could somehow zoom in to the Planck scale, the universe would look nothing like the stable, predictable world we inhabit. Instead of a flat, smooth canvas, you would see a storm. Little tears in space-time form and heal themselves instantly. Tiny pockets of curvature flicker with violent intensity. Particle-antiparticle pairs burst forth, collide, and vanish in a heartbeat. The geometry of the universe warps chaotically, with no two moments alike. General relativity collapses under this chaos, its smooth equations unable to cope with the violent fluctuations. Quantum mechanics, too, is stretched beyond its limit, unable to describe a world where the stage is constantly shifting under its feet. To picture this, imagine the calm surface of an ocean. From afar, it seems flat, serene, stable. But if you place your eyes just a millimeter above the water, you see waves, droplets, chaos, countless tiny events unfold in every second. Quantum foam is like this. The universe appears stable at human scales, but at the Planck scale, it is a boiling cauldron. And this leads us to a profound idea. Maybe gravity does not emerge from a continuous space-time. Maybe continuity is an illusion created by the coarse resolution of our senses. Maybe space-time is built from discrete, indivisible units that flicker and interact in ways we have not yet fully imagined. Quantum foam is the birthplace of the deepest mysteries in physics. It is the arena where a true theory of quantum gravity must be forged. And it is here that two of the boldest theories attempt to rewrite the rules of existence. The need for a new language of nature. The deeper we explore the quantum realm of gravity, the clearer it becomes that our current concepts are insufficient. We are trying to use tools designed for macroscopic intuition to describe a world that defies all instinct. It is like trying to describe music using only geometry, or trying to measure the flavor of food with a ruler. General relativity and quantum mechanics were never built to handle this realm. They were designed to describe very different aspects of reality, and their assumptions begin to contradict each other as soon as gravity becomes strong at microscopic scales. General relativity assumes space-time is continuous, geometry is smooth, distances can be measured perfectly, and energy curves space in predictable ways. Quantum mechanics assumes uncertainty dominates, fields fluctuate, interactions occur in discrete packets, and spacetime is a passive stage, not an active player. At the Planck scale, these assumptions collide violently. The mathematics becomes unstable, equations collapse into infinities, predictions become meaningless. Physicists realize that to make progress, they must create a new language, a new framework capable of describing both quantum uncertainty and geometric curvature at once. This is the birth of quantum gravity. It is not merely an extension of old theories. It is a reimagining of the foundations of physics. The shift is profound as the transition from classical physics to quantum physics a century ago. What if space-time is not a background, but an emergent phenomenon? What if the geometry of the universe is built from something deeper? What if gravity is not fundamental, but a consequence of more basic interactions? Questions like these have driven the development of new frameworks, mathematical architectures capable of describing the universe at its deepest level. And two powerful approaches lead the way. Toward the frontier, enter the quantum landscape. We have now traveled from the familiar world of everyday physics into a realm where space-time loses its identity, where distances blur, where time wavers, where the geometry of the universe becomes a flickering storm. This is the threshold where theories must do more than describe, they must explain. They must unify. They must reveal the hidden structure that lies beneath all things. And so from the swirling uncertainty of quantum foam emerged two profound visions, loop quantum gravity and string theory. Each offers a radically different picture of what space-time truly is. One envisions space-time as a vast network of discrete loop-tiny threads woven together to create geometry. The other imagines the universe built from vibrating strings, minuscule filaments whose oscillations generate particles, forces, and space-time itself. These theories do more than seek mathematical consistency. They attempt to tell the story that unifies the small and the large, the jittery quantum and the majestic gravitational. Now that we've seen the breakdown of our current theories and the turbulence of the Planck scale, we are ready to enter the first great contender, a theory that replaces smooth space-time with a quantum fabric made of loops. Our journey continues with Chapter 3, Loop Quantum Gravity. Weave in space-time, the birth of a radical idea. Imagine space-time as a vast, infinite fabric. Stretch it, bend it, twist it, and yet it is continuous, smooth, unbroken. This is the world Einstein gave us. This is the world of general relativity, elegant and precise. But we have seen how this smoothness fails at the smallest scales. At the Planck length, the continuum dissolves. The smooth fabric of space-time trembles, jittering with quantum uncertainty. And so, some physicists asked, what if space-time is not continuous at all? What if it is woven from discrete threads like the fibers of a cosmic tapestry? This radical question gave birth to loop quantum gravity, a theory that seeks to quantize space-time itself, rather than introducing new particles or hidden dimensions. Loop quantum gravity, or ELQG, imagines the universe as a vast network of loops, knotted and interconnected, forming the very structure of space. These loops are unimaginably small Planck-scale loops, and together they create the geometry of the cosmos. Space is no longer smooth. It is granular, pixelated, composed of these fundamental loops. In this framework, areas and volumes are quantized. They come in discrete chunks, just like energy levels in an atom. There is a smallest possible volume, a minimum quantum of space, and within this granular universe, distances, angles, and shapes are defined by the way loops connect, intertwine, and evolve. Loop quantum gravity is more than mathematics. It is a philosophy of reality. It asks us to reconsider the nature of space itself, not as an empty container, but as a living network. An intricate web whose structure gives rise to the phenomena we observe. Gravity emerges naturally as the dynamics of this web, bending, stretching, and interacting in ways that reproduce the smooth geometry of general relativity at large scales, but resolve the singularities at the tiniest scales. This is the promise of LQG, a universe where black hole singularities disappear, replaced by a finite, calculable core, where the Big Bang is no longer a singularity, but a big bounce, an expansion following a prior contraction, where the very notion of continuous space is replaced by loops of quantum geometry. And it all begins with the simple, elegant idea: space-time is woven from loops. The architecture of the loops. To understand loop quantum gravity more deeply, imagine taking a magnifying glass to the universe. At the largest scales, space looks smooth, continuous, like a calm ocean. But zoom in far beyond atoms, beyond nuclei, beyond quarks, and the ocean is no longer flat. You see a lattice of tiny loops connected in an intricate network. Each loop represents a quantum of space. Each node in the network represents a quantum of volume. Together, they form a dynamic scaffolding from which the geometry of the universe emerges. These loops are not static. They evolve, intertwine, and reconnect over time. Gravity is encoded in these changes. The curvature of space is simply a reflection of the way loops interact. Mass and energy influence the network, bending it, twisting it, shaping it. Space becomes a living fabric, flexible yet quantized, dynamic yet discrete. Unlike string theory, which introduces extra dimensions, LQG remains entirely within the familiar four-dimensional spacetime. There is no need for hidden dimensions or exotic particles. It is a conservative yet revolutionary approach. It keeps the known universe intact while fundamentally changing our understanding of space itself. Predictions from LQG are striking. Black holes no longer harbor singularities. Instead, their cores are composed of dense, finite loops, a kind of quantum lattice where matter and geometry coexist without infinite collapse. The Big Bang is replaced by a big bounce, suggesting that the universe may have undergone a previous contraction, hinting at a cyclical cosmos. Time and space are no longer infinitely divisible. They come in discrete quanta, each a tiny, indivisible piece of reality. LQG also has implications for cosmology. Quantum fluctuations in the early universe may leave subtle imprints on the cosmic microwave background. Tiny ripples in the loop network could influence the distribution of matter on a cosmic scale. And while direct experimental evidence remains elusive, the theory provides a consistent, mathematically rigorous path forward, a bridge between the quantum and the cosmic. Loop quantum gravity is, at its core, a theory of geometry. It tells us that reality is fundamentally relational. Points in space are not independent. They are defined by their relationships, by the loops that connect them. Space is a network, not a stage. Time is an evolution of that network. And gravity is the bending, twisting, and stretching of these loops in a harmonious dance that creates the universe we experience. From singularities to big bounces, one of the most striking features of loop quantum gravity is its resolution of cosmic singularities. In general relativity, singularities are points where the curvature of space-time becomes infinite, and the laws of physics break down. Black holes harbor singularities. The Big Bang begins with a singularity. These points are warnings that our current theories are incomplete. In LQG, singularities vanish. The loops that make up spacetime cannot collapse to zero volume. The smallest units of space provide a quantum cushion that prevents infinite density. Black hole interiors are replaced by highly dense but finite loop networks. Matter is compressed, but it never reaches infinity. The horizon of the black hole remains, but the singularity disappears, a triumph of quantum geometry. Even more radically, the Big Bang is replaced by a big bounce. In this scenario, the universe did not emerge from nothing. Instead, a previous contracting phase reached a minimum volume and then rebounded into expansion. Time did not begin at the Big Bang. It continued through the bounce. This idea is revolutionary. It opens the possibility of a cyclical universe, where expansions and contractions repeat, each governed by the same quantum rules of space-time. The Big Bounce also provides a natural resolution to the problem of cosmic origin. The universe did not spring into existence from a singularity of infinite density. Instead, quantum loops ensure that the earliest moments are finite, well-defined, and calculable. The laws of physics, rather than breaking down, continue to operate at all scales. Challenges and frontiers of LQG. Despite its elegance, loop quantum gravity is far from complete. There are open questions, debates, and ongoing research. How exactly does the loop network evolve over time? How do loops encode the complex interactions of matter and energy? Can LQG make precise testable predictions that distinguish it from other theories? One frontier is cosmology. LQG predicts subtle quantum imprints from the earliest universe. Tiny deviations in the cosmic microwave background, or subtle variations in the distribution of matter, might one day be observable, but detecting these effects is extraordinarily challenging. The signals are faint, buried beneath eons of cosmic evolution, and may require next-generation telescopes or gravitational wave detectors to reveal. Another frontier is black hole physics. LQG predicts that information may not be lost inside black holes, potentially resolving the infamous information paradox. If matter and geometry are both quantized, then black holes become complex but finite systems where information is preserved, encoded in the network of loops. Confirming this requires breakthroughs in theory, observation, or both. Yet the biggest challenge may be philosophical. LQG forces us to rethink our most basic assumptions about space and time. Are they fundamental or emergent? Are they continuous or quantized? Do we live in a universe built from relationships rather than points? These questions push at the very core of human understanding, stretching both imagination and mathematics. The promise of a quantum fabric. Loop quantum gravity offers a radical yet beautiful vision, a universe woven from loops, where space and time are granular, yet classical reality emerges at large scales. It is a bridge across the gulf between quantum mechanics and general relativity, a glimpse of a universe where the tiny and Titanic are reconciled, where singularities are replaced by finite structures, and where the universe itself may be cyclical, rebounding eternally. It challenges our intuition, our assumptions, and even our sense of reality. Space is no longer a passive arena. Time is no longer linear and smooth. Gravity is no longer a continuous curvature, but the result of loops interacting in a cosmic dance. And yet, the theory is elegant, consistent, and profoundly human in its ambition. It reminds us that understanding the universe is not about passively observing, it is about imagining, creating, and daring to see the cosmos as it might truly be. As we explore loop quantum gravity, we catch a glimpse of what the universe is at its most fundamental level, a living, vibrating network of relationships, a quantum fabric of reality, a stage upon which the symphony of existence is written. The next chapter of our journey will introduce an even bolder vision: string theory, the framework that seeks to unify not just gravity, but all of the forces of nature in one harmonious math. Chapter 4. String theory, unifying everything and more, a symphony of strings. Imagine the universe not as a collection of point-like particles, but as a vast orchestra of tiny vibrating strings. Each string, smaller than anything we can perceive, vibrates with its own frequency, producing the fundamental particles we observe in nature. Electrons, quarks, photons, they are all notes played by strings, oscillating in dimensions beyond our senses. This is the central idea of string theory. It replaces the point particles of quantum mechanics with one-dimensional strings. These strings are not static, they vibrate, twist, and resonate. Each mode of vibration corresponds to a different particle, giving rise to the rich tapestry of matter and forces. What makes string theory extraordinary is its natural incorporation of gravity. One of the vibrational modes of a string behaves exactly like a graviton, hypothetical quantum of gravity. Unlike traditional quantum field theories, string theory avoids the infinities that plague attempts to quantize gravity. The framework inherently unifies the forces of nature, gravity, electromagnetism, and the nuclear forces, all emerging from the same fundamental string vibrations. To be mathematically consistent, string theory demands up to 10, 11, or even 26 dimensions of space and time, depending on the version. These additional dimensions are compactified, curled up so tightly that we cannot detect them directly. The universe we experience is just a shadow of a richer, multidimensional reality. String theory transforms our understanding of reality from a three-dimensional stage into a multidimensional symphony. Each string vibrates in a higher dimensional space, producing the familiar particles, forces, and interactions that govern our world. The challenge lies in connecting these abstract extra dimensions to the reality we observe: strings, brains, and the multiverse. String theory does not stop at strings. It introduces brains, higher dimensional objects that can exist in multiple dimensions. Our familiar 3D universe may itself be a brain floating in a higher dimensional space. Other brains, unseen in parallel, could exist alongside ours, giving rise to the tantalizing possibility of a multiverse. Within this framework, everything becomes interconnected. Particles are vibrations of strings. Forces are interactions between these strings and brains. Gravity, in particular, can leak between brains, explaining its apparent weakness compared to the other forces. What we perceive as a fundamental law might be the result of a grander, multidimensional geometry. String theory also introduces dualities, surprising mathematical relationships that reveal how apparently different theories are connected. A theory in one number of dimensions can be equivalent to a different theory in another, hinting that the universe may have a deeper underlying unity. These dualities suggest that reality is not a collection of separate forces or particles, but a single interconnected structure, an intricate vibrating web of strings and brains. This vision is both elegant and daunting. The mathematics is extraordinarily complex. The experimental verification remains challenging, perhaps beyond our current technological reach. Yet the promise is breathtaking, a framework capable of unifying all forces, all matter, and all of space-time into one coherent theory, a true theory of everything, gravity, and extra dimensions. One of the greatest achievements of string theory is its natural inclusion of gravity. In traditional quantum mechanics, gravity resists quantization. Strings, however, smooth out interactions. The extended nature of a string prevents the catastrophic divergences that plague point-like particles. Within string theory, the graviton arises automatically. It is a vibrational mode of the string, massless and spin-2, exactly what is required to mediate the gravitational force. Gravity, once the rebel force, becomes a natural component of a unified quantum framework. The distinction between gravity and the other forces begins to dissolve. All interactions emerge from the vibrations of strings. Their geometry dictates the properties of the strings, determining particle masses, charges, and interaction strengths. In this sense, the shape of the hidden dimensions directly shapes the physics of our observable universe. The universe's seemingly arbitrary constants may, in fact, be reflections of the underlying geometry of the compactified dimensions. This is profound. It implies that gravity, matter, and the fundamental forces are not independent phenomena. They are expressions of a deeper, unified structure, one that may extend far beyond the three dimensions of space we experience. Challenges, criticisms, and the search for evidence. Despite its elegance, string theory faces enormous challenges. The extra dimensions, while mathematically required, have never been observed. The energy scales needed to probe string vibrations are far beyond the reach of any current particle accelerator. Predictions, while theoretically consistent, are often difficult to test experimentally. Some critics argue that without testable predictions, string theory risks being a mathematical exercise rather than a physical theory. Yet its proponents emphasize that string theory provides the only consistent framework currently known that unifies all forces, including gravity, at the quantum level. It resolves inconsistencies that plague other attempts, and it offers deep insights into black holes, entropy, and the nature of spacetime. Physicists continue to explore indirect ways to test the theory. Gravitational waves, cosmic background anomalies, and subtle effects of extra dimensions might one day provide hints. Meanwhile, the mathematical richness of string theory continues to generate new ideas, deep connections, and insights across physics and mathematics. The challenge remains immense, but the potential reward is greater. A complete, self-consistent description of the universe, from the tiniest quark to the largest galaxy, from the beginning of time to the far future of space-time. A vision beyond reality. String theory transforms our perspective on existence. It suggests that the universe is a grand, multidimensional symphony. Each particle, each force, each ripple in space-time is a note played by vibrating strings. The cosmos is not a passive stage, but a living orchestra of fundamental vibrations. The implications are staggering. Gravity, once an outsider in quantum theory, becomes part of the harmonious whole. Black holes, the Big Bang, and the structure of the universe may all be understood as consequences of strings and brains interacting in higher dimensions. Our familiar reality, time, space, matter, forces, is only a projection of a far richer, multidimensional cosmos. String theory challenges us not only to rethink physics, but to rethink reality itself. The universe we perceive is just a shadow of a deeper, hidden structure. And though the journey is difficult, the pursuit is profound, a quest for a theory that explains everything, connecting the quantum and the cosmic in one elegant framework. As we explore the universe of strings, we are reminded that the cosmos is far more intricate, vast, and beautiful than our senses allow. And yet, through imagination, mathematics, and the courage to explore the unknown, we begin to glimpse the underlying unity of all things. Quantum mechanics has illuminated the microscopic world. General relativity has revealed the elegance of gravity and the vastness of the cosmos. The future of quantum gravity is about bridging this gap. Scientists around the world are developing bold ideas, combining theoretical insight, sophisticated mathematics, and cutting-edge technology to glimpse the universe's fundamental structure. Experiments are no longer confined to chalkboards. They occur across galaxies, in detectors buried deep underground, and in massive instruments stretching over kilometers. Gravitational waves, once a theoretical prediction, are now measured with unprecedented precision. The ripples from colliding black holes offer insights into how spacetime behaves under extreme conditions. The cosmic microwave background, a relic of the early universe, carries subtle fingerprints that may hint at the quantum structure of spacetime itself. The challenge is monumental, but the pursuit is inspiring. Each experiment, each observation, each mathematical breakthrough brings us closer to reconciling the quantum and the cosmic. The horizon is vast, but humanity has always been drawn to the edge, compelled to explore, to question, to understand. Experimental frontiers, searching for quantum signatures. The quest for quantum gravity is no longer purely theoretical. Observations are beginning to probe scales and phenomena that may reveal the quantum nature of spacetime. Gravitational wave astronomy has opened a new window into the universe. The collisions of black holes and neutron stars create distortions in spacetime itself. Within these ripples may lie subtle anomalies, deviations from classical predictions that hint at quantum effects. Physicists analyze these waves with extreme precision, searching for the signatures of granular spacetime or the influence of quantum loops. Tiny fluctuations in temperature and polarization could carry imprints of quantum gravitational phenomena from the earliest moments of the universe. Scientists are developing increasingly sensitive instruments, from satellite observatories to terrestrial detectors, to detect these subtle signals. Other experimental approaches include high-energy particle physics and black hole analogs in laboratories. Quantum simulations and condensed matter systems attempt to replicate features of curved spacetime and quantum gravitational effects on a smaller, controllable scale. These experiments may reveal hints of spacetime discreteness, emergent gravity, or other phenomena predicted by loop quantum gravity and string theory. Every observation, every measurement, every new detection is a piece of the puzzle, slowly revealing the quantum threads underlying reality. Theoretical frontiers, bridging loops and strings. On the theoretical side, the journey continues with tremendous creativity and bold ambition. Two major frameworks, loop quantum gravity and string theory, offer complementary perspectives on the universe's deepest structure. Loop quantum gravity seeks to quantize spacetime itself, revealing a granular looped geometry where singularities vanish and the Big Bang becomes a big bounce. String theory, by contrast, aims to unify all forces and matter within a vibrating, multidimensional framework where gravity emerges naturally. Each approach has its strengths, each its challenges. The frontier lies in exploration and synthesis. Some theorists seek connections between these frameworks, exploring whether the granular loops of LQG might be a manifestation of the string's vibrations at certain scales. Others investigate entirely new paradigms, proposing emergent spacetime, holographic principles, or quantum information as the underlying fabric of reality. Mathematics itself becomes a tool of discovery. Advanced geometry, topology, algebra, and even number theory contribute to mapping the quantum structure of the universe. Theoretical physicists walk a tightrope between abstract elegance and empirical relevance, constructing visions of reality that might one day be testable, that might one day reveal the hidden rules behind all that exists. The philosophical stakes. Quantum gravity is not only a scientific endeavor, it is a profound philosophical journey. At stake is our understanding of reality itself. If space and time are discrete, what does that mean for continuity and causality? If singularities are resolved, what happens to our conception of beginnings and endings? If gravity emerges from deeper rules, what is fundamental and what is emergent? These questions challenge our assumptions about existence. They redefine what it means to know the universe. They force us to confront the limits of perception, mathematics, and imagination. In seeking a quantum theory of gravity, we are confronting the ultimate questions: the origin of the cosmos, the nature of reality, and our place within it. The pursuit of quantum gravity is, therefore, not merely technical, it is existential. Every discovery reshapes our understanding, not only of the universe, but of ourselves. Every step toward unification brings clarity, beauty, and insight into the profound interconnectedness of all things. The journey ahead, embracing the unknown. As we conclude this exploration, we recognize that quantum gravity is an unfinished symphony. It is a frontier of imagination, mathematics, and experimentation. The journey ahead is long, uncertain, and exhilarating. Future breakthroughs may come from unexpected directions. Observational astronomy may reveal subtle effects of space-time granularity. Advances in quantum computing may simulate phenomena once thought unreachable. New mathematical frameworks may unveil the hidden symmetries of the universe. And yet, even as we push forward, the journey itself is part of the beauty. Science is a process, a living quest, a collaborative human endeavor stretching across generations. The pursuit of quantum gravity reminds us that the universe is not a passive object to be conquered, but a mystery to be explored, a story still being written. Loop quantum gravity and string theory, experimental efforts, and theoretical insights all converge toward one goal: a coherent, unified understanding of the cosmos. One day, we may discover the framework that reconciles the tiny and the Titanic, that reveals the quantum threads beneath space-time, and that unites the universe's most fundamental forces in harmony. Until then, the journey continues. Humanity watches, listens, calculates, and imagines. The universe awaits, its mysteries vast, profound, and beautiful. And in the pursuit of quantum gravity, we take another step toward understanding reality at its deepest, most fundamental level.